Hello and welcome back to Calculus 1. This is part 2 of 4.5 optimization, where we are continuing working on those word problems which minimize and maximize whatever the objective is. So we talked about it before. We said that these type of problems are all obviously word applied problems, and we are using most of the time we have two equations. One is objective equation, the other one is constraint. We put those two equations together and then we differentiate, which will give us critical points, which in turn are either a minimum or a maximum value for what we are looking for. So let's take a look at more of these word problems and see how these things are solved. So we can start with this problem 37 in the textbook, which has a flower garden given, something like this, and then they say that this distance here is 1 meter and this distance here is also 1 meter, and they have these distances 2 meters and 2 meters. Now meter is about 3 feet, so 2 meters is about, a height of a person. So now they say that inside in the middle it's a flower garden and you want to put the grass all around it, and they would like to calculate the minimum surface area and blah blah blah. Yeah, we don't do that, right? I don't think that even people that do the design for parks do that. But another idea that you can think about, which would have the same type of setup, is when you are designing a pool in a backyard. So you're designing a pool in a backyard and you want to pour the concrete around the pool so kids can run around and fall and scrape their knees. So if you are minimizing the surface area around the pool, that means the smallest amount of concrete used, which means money saved. So all of a sudden this no one uses problem with a flower garden turns into, wow, I can actually save money if I'm trying to install the pool in the backyard. And they do have a constraint, and that constraint says that the surface area inside the pool is supposed to be 30 meters squared. So this might end up being a jacuzzi or a pool, I don't know, we'll see when the dimensions are in. But the question is, what are the dimensions of the pool and what are the dimensions of the outside for everything in order for us to minimize the surface area. So when you minimize the surface area of everything, obviously, when you minimize the surface area of everything and then you take away this 30, they want this to be a minimum, right? But the trick is that we don't actually have to solve area minus 30 equals minimum. We can just solve area equals minimum because 30 is a constant, right? So whether it's there or not there in the formula, it doesn't really matter. Now we'll see where the 30 is used, obviously. But I hope you understand that whether you are just minimizing the concrete part or you are minimizing the entire rectangle, which is much easier, it's the same problem. Now, when you find your dimensions, you can just multiply those, get the area of everything, subtract 30, and you will know how much concrete, what the surface area of the concrete times, let's say, 5-inch thick concrete, let's say, you will know the volume and you know how much to order. But in this case, let's just stick with with the basic calculation of looking for the surface area, to minimize surface area, because that's what the problem wants. So we start with labeling x and y inside, which immediately gives us our constraint, because x times y equals 30 is the equation that we can write immediately by looking at the surface area of the pool, right? This is how much surface area of the water you're going to have inside. Now, I just need someone to tell me mathematically what these lengths would be given the measurements. Tablet, stop moving. There we go. So what would these lengths be labeled as? In terms of x and y, obviously. Come on. It's not a trick question, and it shows over there.
Would it be x plus 4 and y plus 2?
Excellent. So this one over here would be x plus 4, because you see that there is the x length in between the two red lines, and then plus 2 and 2 on each side. So it will be altogether x plus 4. And y plus 2, same deal. On the side, you would have y and then add 1 meter on top and the bottom. And that gives us our other equation where you want to minimize the entire area, where you can say x plus 4 times y plus 2 equals the minimum. Or you can say, minus 30. That was the other way of doing this problem. However, it doesn't change our calculations, right? Because at the end, you will get your x and y anyway, and you would have to subtract that 30. And is also, if you write that minus 30 there, right, the derivative will kill it. So it doesn't matter whether you write it or not. All right, so the steps for solving these were always the same steps. Solve for one of the variables, y equals 30 over x. Take that, plug into the other formula, and have x plus 4, 30 over x plus 2 equals minimum. Work this algebra out, and then differentiate, and there's your x. It is, the procedure cannot be easier, but the hard part is to kind of think about the problem, and this is where your engineering, takes off, actually. Yeah, no one cares if you can compute this, because we have computers to compute this for us. You being an engineer means you are able to set it up. You're able to come up with these equations to, the way to minimize the amount of concrete that goes around the pool. All right, so when we distribute here, x and x cancel, so we just get 30 plus 2x plus 120 over x, and then plus 8 equals minimum. We can differentiate without simplifying, because 3 plus 8 is 38, but both of those are gone with the derivative. So I have 2 minus 120 over x squared equals 0. That's the equation we're working with. So 120 over x squared equals 2. X squared equals 60. And x equals plus minus root 60. Now, we do not care about negative numbers in this case, because lengths cannot be negative. Our x, right, value cannot be negative, so we're just going to take a square root of 60. You can, you can break this into 2 root 15 if you want to have it as the whole number, the exact answer, but 7.75 meters is also okay. And then you have your equation for y, which was 30 over x, so 30 divided by 7.75, and that one is going to be 3.87 meters. So the dimensions of the entire thing are 7. Doesn't matter which one you list first, but we are used to listing the larger number first for rectangles. So this would be the size of the pool, and if you multiply these two numbers, you should get 30. I mean, that's or very close to it, because we rounded, and that's the meters. And then you can use these two numbers in this equation, which would give you the area for the whole thing, and you subtract 30 to find the area for the concrete only. So that's the part where, again, you are ordering concrete and all of these things. Now we just wanted to find x and y dimensions, and then we can construct everything else, because once you have x and y, you measure 1 meter out, 1 meter out, 2 meter and 2 meter, right? And then you just set the edge for where the concrete is going to be poured and leveled, and that's it. So it's a very simple procedure after that. So if you're able to come up with these equations, yeah, you're good to go. Another problem. So we talked about the box. We talked about this. Minimum distance to the curve. So again, this is something that is cool. So find the point on the curve y equal x squared, so that it's the closest to the point 18.0. Again, a lot of applications for this, because you are calculating the minimum distance between the point and the line graph or a function. So, and that this can be very useful, right? There we go. In many cases, in many applications. So you have your x squared graph, and then you have 18, 0. So that's 18 on x-axis. And they are looking for the closest distance to the line. So that's going to be something like this. Let's call that distance d. So they are looking for this point here, which we don't know, xy, so that this distance is a minimum distance. Now, since we are on the flat surface, obviously that distance is the straight line. On the curved surfaces, that distance is not a straight line. So when you see the airplanes, right, if you have the planet, you have the US over here, and then you have a Europe over here, and let's say you are flying to whatever, Paris, let's say, from New York, the plane will take the curve like this. Well, that's the shortest distance on the surface of the planet, because the planet is a sphere, right? And the shortest distances on the sphere are not straight lines. Straight line will take longer, right, to go. If you just go straight across, it would take longer to get there, and you would use obviously more fuel and more time and more everything. Now, in order for you to learn about that, you have to take the Calc3, you have to learn about hyperbolic surfaces and a whole bunch of other cool things to understand why and how. Also, triangles on the curved surface do not have 180 degree, right? They add to more or less than 180 degrees, where on the flat surface, triangles always add to 180 when you add their angles. And you can also use planet Earth to kind of see that, because or just take a regular ball, put the North Pole and your equator, and if you walk straight down, turn 90 degrees, walk 1/4 of the length of the equator, stop, turn 90 degrees again, and walk up. So if you walk in this pattern, you have 90 degrees and 90 degrees, and you still have the third angle on top. So you already used 180 on the equator. You used 180. Well, if you walked 1/4 of the Earth on the equator, then the top angle is also 90, and you get 270 degrees, right? It's kind of cool. Think about it. If you have the surface of, and this is your North Pole on the top, and you walk 1/4 of the equator, so you went this way, you went that way, you went this way, then you see that it's 90 degrees on the North Pole as well, right? Because you went 1/4 of the equator's length. So when you now see this, right, you say, oh, wow, right? So all of the stuff that I know for the triangle doesn't really hold in a real world. No, it does hold, but it's only on the flat surface. Geometry, holds for the flat surface. It doesn't hold on curved surfaces. So that's a little bit aside, so you can research and hopefully, right, take Calc3 and try to see these kind of things. So on the flat surface, the shortest distance between 2 points is straight line, and that's why we have this straight line connecting x and y, which we want to find, and this one. Now, clearly, right, the relationship between x and y is our constraint, which is y equals x squared, and that's ready to be plugged in. And we have the distance formula, which is x2 minus x1 squared plus y2 minus y1 squared between the 2 points. And we do have one of these points to be 18, 0. So we can rewrite, and the other point is x and y. So plug them in. And I don't really care which one is your first and what one is your second point. It doesn't matter. So we'll have 18 minus x squared plus 0 minus y squared. Uh-oh. We are experiencing overheating, so I'll have to go get the cooling already. Wow, we didn't even make it like 30 minutes. So, not even 20 minutes, and it's already getting toasty. And you guys have your substitution, right? So this thing goes in there, replaces that y, and then you can just differentiate. Oh, I forgot to say equals a minimum, right? Because I am minimizing. This is my objective function, so I have to have min and max. All right, so I'm going to get the cooling. You try, go ahead a little bit with this problem, plug that in, and work out some algebra so we can take the derivative. I'll be right back. Okay, so we have our equation. So we're going to expand everything. So 18 squared is 324 minus 36x plus x squared, and then plus x to the fourth equals minimum. This 0 minus 2 will be negative y, so you get negative x squared. When you square everything, it kills that negative there, and it becomes x to the fourth. So now we are ready for the derivative, and when you take the derivative, you get the it's a square root, right? So it goes 2 times the same square root in the bottom, and then its derivative on top, which is 4x cubed plus 2x minus 36 equals 0. And now, when you cross multiply, the denominator completely cancels, and if you cancel it by 2 as well, right, you get 2x cubed plus x minus 18 equals to 0. Now, this is not 2x squared. It is 2x cubed, which means evil, right? It's a polynomial. Then we have to solve and so on. So I don't want to waste time on looking for rational zeros and all of that stuff. I mean, on the exam, sure, you look for rational zeros, you try to factor this thing, you try to find the values. I'm just going to use a tool real quick because I don't want to spend another 15 minutes on that stuff. So I'm going to just use a quick tool to solve this. So we have 2x cubed plus x minus 18 equals 0. And the value that we get from this is x equals 2. See, factoring would work out great. So we get, and then we get two complex numbers that we don't care about. So when you solve this, you get x equals to 2. And now that I have this, I can calculate y, and y was x squared, so 2 squared, and it's equal to 4. So the closest point is 2, 4. Any other point on that parabola will be further away from 18, 0. Now, obviously, if you change 18, 0 to a different location, then you are going to have, right, if you change it to any other location, you are going to redo the whole calculation because the formulas change. As soon as I change this 18, all of the numbers in here change, and then clearly everything else. So I have to redo this problem from scratch. So this problem was, you have a point given and you have a function. Think of it as a path. Or if you want to throw something to someone running on a path or something, what is the shortest distance, right, for your throw? I mean, we don't compute those things really, but I'm going to show you a distance problem that you can obviously make money with. So let's talk one of these business applications. So over here you have some kind of seashore. So this side is a shore, there's a sea on this side. We're going to put some kind of oil refinery here or whatever, right, where you put the unprocessed oil to, change it into technically everything we use, which is gasoline and diesel and the plastic and rubber, right? So technically all of that stuff is coming from oil. I mean, there's a lot more applications, but let's just, say those. And you're going to have some drilling platform over here. So drilling platform, oil rig, right? And they are drilling for oil offshore. Now, the distance to this platform is 5 miles, and the distance this way down the shore is 10 miles, let's say. I'm just making all of these up, doesn't matter. And you are not going to run a tanker ship between these two. It's way too close. So you might as well lay pipes and just directly supply. Now, once you drill out everything and you disassemble this and move it and it's gone, the factory will still be there and the ships, will keep bringing stuff in and out. So it's not a, so this stays in its location. The other one might be moved once everything is drilled out and gone. But for now, for years, right, we're going to be drilling and extracting from there. So, we might as well lay pipes so we don't have to run the ships back and forth. Those ships are a big issue, right? Because they you can go online and look how many times the ships would break, something would happen, and they would spill oil into the ocean. So that's not it's not good to bring the oil from long distances, right? That's something that is environmental concern. So let's say we're going to build the pipes and not run the ship, which is good. Now you have the pipes that are on ground. That's these pipes here are on the ground. The other pipes that are here are the pipes that are underwater. Now, it's not the same cost to put the pipes under the water and to put the pipes on the ground. Now, I am going to also say that this is the shortest distance, and we don't have to worry about curvature of the earth, on a 5 mile distance there, or whatever the Pythagorean theorem gives us here. Oh, I've seen such a funny meme about this social distancing, where they have four corners like this, and it says between here and here 6 feet, between here and here 6 feet. Oh my god, people are so dumb. And then this one 6 feet, and this way 6 feet. And then there is that situation where they're trying to hold back Pythagoras, saying, cool it down, cool it down. Anyway. Oh, that it was awesome. I saw that, I think 2 days ago. Anyway, so we have the option of running the pipe shortest distance, which is straight through to the shore, and then down the shore to the refinery, or through the water. Now I'm going to make up these numbers just to so we can talk about cost and put some numbers down there. So I'm just going to say the cost is, let's go with I don't know, let's go with $500,000 for 1 mile of pipe underwater. I'm making this up. I don't know how much it is. This might be too cheap for 1 mile to lay the pipe under the water, because yeah, it's not easy. And maybe how 200,000, 250? I don't know, $250,000 for 1 mile of pipe on ground. Find route to minimize cost. So what is the best route to minimize cost? Now, what I have here are black and blue routes. Let's call the black route route number 1, and let's call the blue route route number 2. Now, the black route, very simple. You have 10 miles of pipe on the ground, so 10 miles times $250,000, plus 5 miles at $500,000, and that gives you the cost for the black path, path number 1. So that's 2.5 million, 2.5 million, altogether 5 million to make the path. So when you look at the black path, right, you say, okay, $5 million and I can create this path easily. Now, the blue path is also something to consider. You do not have on-ground pipe at all, but the blue pipe is the shortest distance. Maybe that one is going to do better, right? So now we first have to figure out that distance, right? D, and D squared is equal to 10 squared plus 5 squared by Pythagorean theorem. So that's 125. And the distance, when you take a square root, again, ignoring positive, negative, is going to be about 11, right? Because square root of 129, sorry, or 121 is 11, so square root of 125 has to be like 11.1, 11.2, and using the calculator, it's 11.18. So now the cost for the blue route would be 11.18 times, it's $500,000 for each mile of that, so times $500,000 is going to give us 5.6 million. So it's 5,590 and then 169 and 94 cents. Who cares? So we're just gonna round it off and say it's, you know, almost 5.6 million. So you see that even though it's the shortest distance, it's actually worse, right? Because the pipe underwater costs much more than laying a pipe on the ground. And now you would think, right, that the big boss would say, let's go and build the $5 million one because it's obviously 600,000, almost 600,000 cheaper. But then you as a contractor say, hold on. How about if we go a little bit on the ground and then cut through the water like this? So if we are able to figure out this situation and find X and L so that the cost is minimum, maybe we can go under $5 million. And the person says, okay, let's see, right? So you do this calculation, and now we are supposed to figure these things out. Now, clearly, what you are minimizing is the above ground pipe with length X times 250,000 for each mile, plus underwater L, length of the pipe in miles, times $500,000 per mile, needs to be a minimum. So objective for this third route is to minimize cost, and that is very simple. Your above ground cost times X plus underwater cost times L needs to be a minimum. So that's your objective, right? You want to minimize the cost of this. Now, all we need to do is to find our other equation, right? The constraint, which is equation that connects x and L, and we are done. Now, yeah, I do have that this D is 11.8 and blah, 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 but that doesn't really help me because this triangle is not a right triangle, so I can't use really Pythagorean theorem on the red-blue triangle. But if I use a red-black triangle, which is a right triangle, I can actually make the connection between 5 miles and L, and then I just need this length here. So does anyone see what should I label this length as in terms of whatever variables?
10 minus x.
Beautiful, 10 minus x. And that's where you, as soon as you realize that this is 10 minus x, you guys are done. Now you have your Pythagorean theorem, 10 minus x squared plus 5 squared equals L squared. So, constraint is 10 minus x squared plus 5 squared equals L squared. And you can clearly solve this for L, plug it in there, differentiate, and you will have your x. You can calculate L and pocket the money. So, from this equation, L is equal to the square root of 100 minus 20x plus x squared plus 25, which is the square root of x squared minus 20x plus 125. And now you stuff that into the equation up there. So what you get is 250,000 times x plus 500,000 times the square root of x squared minus 20x plus 125 equals the minimum. And once you differentiate this, you're done, right? Because that will spit out your x as a number, right? Whatever it is. So you differentiate this, and that will give you the x that minimizes the distance x. Then you have the way to compute L. You just use this with the x you found, and you compute L. All right. So what's my derivative here? It's a quarter million. Derivative of x is 1 plus 500,000 times, and now the derivative of the square root is always 2 times the same square root, and then the derivative of this square root goes on top, which is 2x minus 20 equals 0. Now, when you cancel this and this, you get quarter million, and then you divide the entire problem by quarter million. All of those quarter millions are gone, and you have 1, right, plus 2x minus 20 divided by the square root of x squared minus 20x plus 125 equals 0. Now, to solve this, you move 1 to the other side. It becomes 2x minus 20 over the square root equals to negative 1. You multiply both sides by the square root, and you get 2x minus 20 equals to negative square root of x squared minus 20x plus 125, at which point you square both sides, and now on the left-hand side you have 4x squared minus 80x plus 400, right? So that's 4, 2 times 20 is 40, times 2 is 80. Okay, good. Usually students forget the middle term and then the whole problem goes to hell. Just, you know, if you don't know the formula for squaring the binomial, FOIL it on the side and get it right. Now the square will kill that minus and will kill the square root, so you just have this x squared minus 20x plus 125. Move everything to the same side, you get a 3x squared minus 60x, and then this, when you subtract 275, so plus 275 equal 0. You can use quadratic formula, you can use online tools, whatever. I'm just going to jump real quick so we don't waste time here. Minus 60x plus 275 and x equals, I need approximate form, there we go. So x equals 7.132 or x equals 12.887. Now, guys, remember that x was along the shore and the shore is 10 miles long. Remember that this is 10 miles long. So can x be 12.887? The answer is hell no, right? So we drop this answer because shore is 10 miles and we have the answer that we want for x. Now we calculate the length under the water, and that was the square root of x squared minus 20x plus 125. X squared, was it minus 20x, okay, minus 20, okay, plus times 7.1132, 125 over here. L equals, I'm allergic to these calculations, 7.1132 squared minus 20 times 7.1132 plus 125 is 5.77 miles. So we got that we need, let's go 7.1 miles on ground and 5.8 miles underwater, which gives us the cost of what? Well, you have your 250,000 times 7.1 miles plus your 500,000 times 5.8. So now let's see what that is. So 250,000 times 7.1 plus 500,000 times 5.8 to give us 4,675,000. There we go. So the red one in comparison to black one, right? Remember that black one was 5 million flat, right? So black one gave us 5 million. Blue one we already x'd out because it was more than the black one. And now with the red calculation here, we are saving 325,000. So So they're gonna give you 10% of that, right, for your troubles, for your 15 minutes of trouble, and you there you go. You make $32,000, like 32 and a half thousand, right? That's a 10%. They keep 90 in the pocket, and yeah, this is how you make money with these things. It's very simple. Um, Calculus is used, obviously, as we said, everywhere, and yeah, the rest is you guys going and trying to figure out these problems. Um, Companies, right, constantly optimize. It's called optimization, right, where you look for the optimal solution. Remember, we minimize the surface area of the box to minimize the amount of material required to make the box, which reduces the cost of boxes because you make million boxes, let's say. So 5 cents times a million is a huge saving to the company. And a lot of things like this pop up constantly, and the hope is that right, you can um, perform, right, that you can learn enough to be able to work in the field. So very simple problem, as you can see. We just use Pythagorean theorem and about 15 minutes calculation to cash in $30,000, right? They give you 10%, let's say, um, as a contractor of what you save them. All right. Well, that's optimization. We're going to take a short break, and then when we come back, we have more tangent lines to talk about. Any questions, concerns about optimization problem? Any optimization problem we did, or maybe something we didn't do? You run into homework problem? Nothing? Okay. Then I will see you when we come back.